Hi, welcome to Fibonacci Numbers, Patterns and Problem Solving, one of my favorite sections in this problem solving unit. The Fibonacci numbers start like this, 1, 1, 2, 3. What do you think the next number is? It's really hard to tell with just this small a pattern, but see if you can make a guess, even a wild guess. Now let's look at the next number. The next number is 5. Did you guess 5? Did you guess 6? Did you guess something else? That's fine. But now that we have one more number, you can start refining your idea of what the pattern might be. So what do you think the next number might be? This is a game called Guess My Rule that's great to play in grade school with simpler patterns or even with shapes like triangles and rectangles. And you see if the kids can guess the next shape in the sequence or the next number in the sequence. It's a lot of fun. And you can play it silently so that a student is allowed to come up and write the next shape or next number in the pattern, but they're not allowed to say what the pattern is. That gives other students a chance to also try to guess the pattern without being told. It gives more thinking time. So let me tell you the next number in the pattern, and then give yourself some more thinking time if you don't see the pattern yet. So the next number in the pattern is 8. Do you see what's going on in this pattern? Pause the video if you haven't already and see if you can figure it out. For the next number, we have 13. So the pattern is now 1, 1, 2, 3, 5, 8, and 13. If you haven't guessed the pattern yet, think about looking at the previous two numbers and then this number. Or look at the 2 and the 3 and then this number. The 5 and the 8. And this number. Now what do you think the next number is going to be? If you haven't already, pause the video and see if you can figure it out. So the pattern is that we add the two previous Fibonacci numbers to get the next one. For example, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, 8 and 5 is 13. So now you can guess at what the next one's going to be, right? Look at the 8 and the 13 and see if you can figure out the next one. And I'll tell you in a minute if you're right. So the notation for Fibonacci numbers uses subscripts. So for instance, F7 means the 7th Fibonacci number. And what I'd like you to do is get the next Fibonacci numbers, F9 and F10. So F7 is 13 right here. So I'd like you to try to get this one. That's going to be F8. And then keep going so you can get F9 and F10. Pause the video until you've gotten all three of those. So the next Fibonacci numbers are here. They should be 21, 34, and 55. So that means that F9 is 34 and F10, the 10th Fibonacci number, is 55. In general, if you do a web search for Fibonacci numbers, you're going to get a huge long list of them. So if you need a huge long list as you're working on the project or on the homework, you can easily find them, like this one on Wikipedia. It goes all the way up to F20 here. And look at how it starts. It starts with 0 instead of with 1. That's because if you do 0 plus 1, you get 1, right? And then 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, and so on. Why are they called Fibonacci numbers? That's this guy here in this picture. This is Leonardo of Pisa, who was also known as Fibonacci. He lived in Italy in 1202. They also appeared over 1,000 years before that in Indian mathematics in Sanskrit poems, which is pretty typical of mathematical discoveries, that they're discovered over and over again through the centuries. I want you to pause for a second and notice something about this guy's name. Leonardo of Pisa just means he was this guy named Leonardo from Pisa. So you can see why he would have to have a nickname like Fibonacci. I'm sure there were lots of Leonardos from Pisa because they didn't have last names back then. So the cool thing about Fibonacci numbers is that you can find them in nature and in art, like in flower petals. Here's one with 3. Here's one with 5. Here's one with 8, 13, and it just keeps going like that. This is the Trillium, the Texas yellow star with 5 petals. And on, I bet you know the Black-eyed Susan with 13 petals. Chicory, daisy, and the one with 55 looks like another kind of daisy. I have no idea. But they're very pretty, right? And most of these flowers come in Fibonacci numbers. Also spirals in things like sunflowers, pine cones, artichokes, and pineapples tend to be Fibonacci numbers because the most efficient way for the spiral to grow, just like petals, the most efficient way is to grow in Fibonacci numbers. So if you listen to the Vi Hart video that's next, she explains really well why that happens in a really artistic way that's a lot of fun. I just want to show you right here for a second. See the spirals in the pine cone? Like this? So here they are drawn out. This is 1 spiral, 2 spirals, right? 3, 4, 5, 6, 7, 8. I lost track. Yeah, that was 8. That was 8 spirals going in the red direction and then 13 spirals going in the blue direction. So that's 2 consecutive, one after another, Fibonacci numbers. So now I'm going to talk about the golden ratio. If we take the Fibonacci numbers and we divide 2 consecutive Fibonacci numbers, that means Fibonacci numbers that are one right after the other. For example, if we do F4 divided by F3, that's 3 divided by 2, we get 1.5. Let's see what F4 is, the 4th Fibonacci number. 1, 2, 3, 4. So that's 3. And then F3 is the 3rd one. 1, 2, 3. So that's 2. If I try dividing the next pair, and I want you to do this with me, so you could pause the video for a second, find your phone or your calculator and try this one. F5 divided by F4 is 5 divided by 3. See what you get on your calculator. And then try the next pair, F6 divided by F5, which is 8 divided by 5, right? Because 1, 2, 3, 4, 5, 6. The 6th one is 8. And then the 5th one is 5. 8 divided by 5. See what you get. You're going to notice a really interesting pattern happening of your result. And I want you to keep going. So keep going up until you divide all the pairs that you see up there and see what happens. Go ahead and pause the video. So what do you notice is going on with those results? As you divide larger and larger Fibonacci numbers, you should be getting 1.6, 1.66, and then it goes down, goes up. It tends towards the golden number phi, which is 1.618033, goes on and on and on forever. It's called phi, and it's an irrational number like pi. Irrational, meaning that the decimal part goes on and on forever like that. There's no fraction that you can write of whole numbers to equal phi. But we do have this fraction. It's not whole numbers. It's got a couple of numbers in the top. This one is a decimal. But don't worry about the formula. I just wanted to show it to you so you could see there is a formula for phi, but you don't have to know it. The Greeks thought that things were in this ratio were more pleasing to the eye. So here's the Parthenon. And if you take A, the distance across the bottom, and B, the height, and divide them, you get approximately phi, the golden number. The Renaissance painters used this golden number in their paintings. So this is the Mona Lisa by Leonardo da Vinci. It's another Leonardo. That means he's Leonardo from Vinci. And he made this painting so that her face was in the golden ratio, or phi. And if you measure your fingertip to your shoulder divided by your fingertip to your elbow, you will get something approximating the golden ratio. I have tried it in a lot of classes and it works. It's kind of awesome. So we're going to use subscripts to find patterns in the Fibonacci numbers. So let's just talk about subscripts a little bit more before we look at the pattern. Do you remember what F12 means? F12 means the 12th Fibonacci number. And that 12, the little number, is called a subscript. We say F12 is the sum of the previous two numbers. That's F12 is equal to F11 plus F10. That's the 11th Fibonacci number and plus the 10th Fibonacci number. In other words, 144 is 89 plus 55. Since those are the 12th, 11th, and 10th Fibonacci numbers. Notice that 11 is 1 less than 12, and 10 here is 2 less than 12. You're going to use that pattern to get the general formula. So we could write 12, 12 minus 1, that's 11, right? F12, F11, and F10. We're going to imitate that with the letter N. So if we put an N here, we're going to do the same thing to N that we just did to the 12. We're going to have Fn, Fn minus 1, just like 12 minus 1, and Fn minus 2, or 12 minus 2. In general, that's how you get a formula. You imitate what's happening with the numbers with your variable. And so that's what we're going to do throughout the next couple of examples. So let's look at what happens with the golden ratio, and let's see if we can get a formula for that. So these are the golden ratio numbers. So I want you to look for a second at what's always happening with these two numbers, and we're going to imitate that with N. So what do you notice about the 5 and the 4? What do you notice about the 6 and the 5? If you let the 5 be N, what would this one be? So notice that the bottom number is always 1 less than the top number, right? So pause the video for a second and think, if I let this top one be N, what would the bottom one be? You might want to write it down. Write down your guess. And imitate it using N. Here we go. The general formula is Fn over Fn minus 1. We could have also started with the bottom number as our N, and then the top number is 1 more. If that makes no sense to you, don't worry about it. All I'm doing is saying that there's always going to be more than one, or often going to be more than one correct way to write a formula, depending on what we take N to be. If you got it one way, that's fine, though. You don't have to write all the possible ways. Now let's look at another example. We're going to add any 6 Fibonacci numbers and see what pattern we notice. So 6 consecutive Fibonacci numbers. That means one right after the other. So for instance, the first 6, F1, 2, 3, 4, 5, and 6. We get 20. What if we add a different 6 consecutive numbers, one right after the other? You could pick any 6 you want that are one right after the other. So you could add F3, 4, 5, F6, F7, and F8, and you get 52. Here's another 6. Again, they're all consecutive, right? They go one right after the other. You can pick any 6. They can overlap with the previous 6. They can start a new batch. And now let's look at what pattern we have. So in terms of this pattern, I want you to look at these answers, 20, 52, 136, and see what the largest number that you can divide into these numbers would be. So what goes into 20? What's the largest couple of numbers that go into 20? And then what are the largest numbers that go into 52? 2? And is one of them the same as the one that went into 20? And then see if you can divide 136 by that number as well. And 220 by that same number that went into 20. Then see if you can write each of these as a product. So 20 is what times what? Remembering that you're taking the largest two numbers that go into 20. So don't use 2. Use a larger number than 2 that goes into 20. And see if you see a similarity between these 4. Pause the video for a second and try it out. Or if you're not sure you want to pause yet, there will be another chance to pause. So each one is divisible by 2, but you can divide each of them by 4, the largest one that goes into every single one of those. So if you didn't get it already, try that out now. And you're writing 20 as 4 times 5. So now go back to the other examples and see if you can write the other examples as 4 times a number before you go on. So pause the video. You should find that you get 4 times a number for each of these. 4 times 13, 4 times 34, and 4 times 55. To see more of the pattern, check out these numbers right here. These are all a special kind of number. Do you notice what kind of number they are? See which Fibonacci number each of them is by writing down the subscript. So 5 is F what? 5 is F5, right? Then 13 is F what? And just write that down next to the number. So this first one is 4 times F5. The second one is 4 times F7. Next one is 4 times F9. And this one is 4 times F10. And I want you to start looking at these Fibonacci numbers and seeing if you can tell which Fibonacci number these are in relation to what you just added here. And what you should be able to see is that this is 4 times the 5th one. The 5th Fibonacci number of the ones I just added. This is 4 times 1, 2, 3, 4, 5. This is the 5th Fibonacci number right here. And again, 1, 2, 3, 4, 5. This is the 5th Fibonacci number right here. So using subscripts, if this one is n, this one's going to be n plus 1. See if you can write it all out with its subscripts, including the answer of 4 times f. And then what would you put in the subscript that would have n in it? So pause the video for a second and see if you can figure it out. You should find that you have fn, fn plus 1, n plus 2, n plus 3, n plus 4, n plus 5. And that it's always 4 times n plus 4, which is this Fibonacci number on your list. So I want you to try that kind of thing in our Fibonacci patterns, in our homework, and on the project. And I think you'll be really excited about the kinds of Fibonacci number patterns you can find. And some of it might be kind of hard too, right? I think it's not as interesting until you work at it a little bit. So remember, we're all here to help each other. Remember, you can shoot me an email if you get stuck, talk to me if you get stuck, and let's find out some interesting patterns.